Once around Supernova 1181. Well, this story starts in the year 1181 on the 4th, 5th, or 6th of August, and Chinese and Japanese astronomers noticed what they called a guest star, a star that had suddenly appeared in the sky that wasn't on their star maps. And in fact, there are 8 separate texts from that time that record the event. It's not entirely clear from any of them exactly where the star was in the sky, but by combining all of them together, we figure that it's inside the ellipse marked in the red color on the diagram there. Somewhere inside that ring is the area in question. It's towards the north, and it's slightly north, in fact, of that zigzag pattern, which you may recognize, because this is one of the 5 observations of a supernova before the invention of the telescope that's been subsequently confirmed. And that zigzag pattern, well, that is the constellation of Cassiopeia. And this particular event, SN1181, was visible in the sky as one of these guest stars, getting brighter and then fading away slowly for about 6 months, 185 days. And that's a fairly typical duration for one of these events. When we look back now with a modern telescope, in this case, the 2.4 meter Kitt Peak telescope, then we can see this amazing radial pattern coming from a central region here. Now, this picture's in the negative, so the bright regions are showing as black, so the bright dots are stars, and we have this streaks of bright matter coming away from the center. And the region in question, just above the W of Cassiopeia, is roughly where the blue cyan colored region is, with various different constellation names from different cultures marked on the map there, and different stick diagrams overlaid. And a couple of things with red crosses that might well have been, and in fact have been postulated as the exploding object or the remnant associated with the explosion. 3C58 and PA30, they're indicated there. So 3C58, this is a radio source that was picked up in the 3rd Cambridge Radio Survey using an instrument that sadly is no longer there. And the whole observatory upsticked and moved to its current site at the Mallard Radio Observatory south of Cambridge for the 4C survey, but that 3C survey was abandoned. But it produced this catalogue, and number 58 in the catalogue is a pulsar, a neutron star rotating 15 times a second and giving out X-rays and radio waves. And there's a modern image zoomed in of it on the right there. Now, the position of this location has been pinned down today with optical telescopes and high-resolution aperture synthesis radio telescopes, but the 3C survey, using the wavelengths that it did and the instrument that it did in the very early days of radio astronomy, wasn't able to locate things to better than a degree or so on the sky. So it could well have been that 3C58 was lined up with the position recorded by the Chinese and the Japanese. But when studied, we find that it probably isn't, because the age is wrong. The radio flux coming from the emissions from the pulsar is declining, and that's a little difficult to estimate the age from, but you end up with a figure around 3,500 years, and that's too long. These pulsars spinning around at the moment, it's spinning at 15 times a second, but they gradually spin down as they radiate energy and angular momentum away. And so the spin down age comes out even longer at 5,800. And the temperature, well, neutron stars lose heat over time, so they should cool. And this seems to suggest an age of around 5,000 years. So definitely too old for SN1181, because that was only about 1,000 years ago. So this just doesn't fit. We've also measured the distance, and it seems to be about 30% too far away at 10,000 light years compared to around about 7,000, 8,000 that we have for SN1181. Now, it's difficult to estimate the distance of a nebula, so there's a little bit of uncertainty there. The other object, PA30, discovered in 2013 by Dana Patchik, she was looking for planetary nebulae using the WISE infrared telescope. And the image of PA30 shown on the right looks like a planetary nebula. It's about the right size. It's about the right sort of shape. There's a central, very blue star and a ring of material expanding away from it. Just what she was looking for. But, well, let's have a look. So Gaia has measured the distance and got 7,500 light years. So that seems to be a good fit for the supernova event. It's bright in the infrared, and you can detect the optical component. Here's another optical picture using oxygen 3 and showing this lovely green color as a result, showing that central star with the material radiating away from it. And in X-rays, the XMM Newton telescope from the European Space Agency and NASA's Chandra combined to produce this image, showing a very hot central region and a rather larger area of more diffuse but very hot matter around it. So that's perhaps not quite like a planetary nebula. You don't normally see quite such an extent of X-ray emissions. And the X-ray emissions can tell us things about the composition of the nuclei that are present in the nebula. And it reveals neon, magnesium, and sulfur and silicon, all products of later stages of fusion. Carbon-carbon fusion produces neon and magnesium, for example. But when you delve into this shell of X-ray emitting matter in more detail, you find there are two rings of X-rays coming from it, an inner shockwave where the termination of the stellar wind coming from the central star is being brought to a halt by it impacting with the surrounding material, and an outer ring where the outer traveling ejector from the event is hitting the interstellar medium and creating another shock wave, leading to another bit belt of X-rays. And in between the two, we have a warm dust ring. And so this looks like an expanding shock front and a very hot central star. And indeed, the central star is immensely hot, 200,000 Kelvin, one of the hottest stars that we've ever seen, hotter than most typical white dwarfs. Those are usually up to about 125,000 Kelvin, but this is even hotter. And it has a very, very powerful stellar wind coming away at 16,000 kilometers per second. When we look at the spectrum, we don't see hydrogen or helium. We see the outer layers of the central star being carbon and oxygen. And all of that points to this being a supermassive, highly magnetic white dwarf star. So a star that has got significant mass, probably heavier elements than carbon and oxygen in the core, and late stage in terms of having lost all the hydrogen and helium from the outside, just due to that extreme temperature. Now, we can also see the expanding shell of material moving using the Doppler effect, and that gives us a speed of expansion of around 1,100 kilometers per second. And that's good because you can work backwards from the size, and it works out to be about 1,000 years that this stuff has been traveling. And that's in good agreement with the date of 1181, just about 1,000 years ago. So it seems highly probable that PA30 is the result of the supernova event. That's further confirmed by the fact that X-ray studies show that we have some medium weight metals present. In particular, we can see the presence of the decay chain of nickel 56 decaying through cobalt down to iron. And you can see the energy diagram here. Nickel 56 captures an electron, turns into a series of excited states of 56 cobalt, which capture another electron and then turns into iron 56, again through some excited states down to the ground state. So there's this energy ladder giving off lots of energy as it goes. Now, normally the nickel 56 captures an electron with a half-life of around 6.5 days. And it's responsible for the very strong peak in the spectrum of a type 1a supernova. You can see where it says Ni at the top of the light curve there. That is the nickel 56 responsible for the energy output there. And then that decays quite quickly, and then the decay slows down as we get to cobalt, and the cobalt decay takes longer, 77 days, to decay to iron, so the curve declines less rapidly. But in this particular object, what we're observing is such a high temperature that the nickel present is completely ionized. All the electrons have been stripped off, so there are no electrons orbiting close to the nucleus for it to capture. And so instead of 6 days, that electron capture reaction is taking hundreds of years and slowing down the power output of the radioactive decay chain here by a significant amount, causing a completely unusual curve in the decay of the light coming from the event, which definitely makes it look very unusual, not a typical type 1a supernova at all. Now, we also find that the explosion is asymmetric. There are red shifted filaments on one side that are brighter than the blue shifted filaments on the other side. And this suggests that there was perhaps a merger as the trigger, and that in the merger, the resulting explosion has ejected the residual star in one direction away from the nebula, and it's moving through it. But there are other possibilities. That merger just could have been of two white dwarf stars. Perhaps what they were different, one of them being an ordinary carbon-oxygen white dwarf, lower mass, and a slightly more massive oxygen neon magnesium containing star, and that would explain some of the elements in the spectrum that we see, and perhaps that's really what's been going on. So when these white dwarfs explode, the type 1a supernova, the normal explanation is given that they accrete mass, and that can usually be from a binary pair. One of them evolves into a white dwarf quicker than the other because it's more massive. The second one catches up and can turn into a giant, lose mass. The giant has relatively weak grip on its outer layers, and so some of it spirals onto the white dwarf, and indeed the result can be that that then tips it over the Chandrasekhar limit. Or sometimes you end up with the entire envelope being stripped away into a disk, and then what can happen is that the white dwarfs can orbit each other and spiral down and merge. But this isn't quite the whole story, because in fact, you don't have to wait for the Chandrasekhar limit. Just below the Chandrasekhar limit, just 1% below it, we think that conditions, depending on what the star is made of, can reach the point where carbon can start to undergo a runaway fusion reaction, liberating vast amounts of energy. Now, at the Chandrasekhar limit, this probably happens, but it can happen just before it as well. And what happens is that two carbons combine to make magnesium and some other elements. The first thing they do is make an excited magnesium atom or nucleus, with a little bit of extra energy. So you get 12,6 carbon plus 12,6 carbon makes 24,12 magnesium with that extra energy. That's what the little star at the top there means in blue. And that dumps the energy by nuclear decay. And there are 5 different paths. The simplest one is for it to just dump the energy as a gamma ray and make 2412 unexcited magnesium. It can split up, leaving 16,8 oxygen and 2 helium nuclei, alpha particles, 42Ag. Or it can split into a neon nucleus, 2010 Ne, and 1 alpha particle, 42 helium. Or it can spit out a proton and turn into 2311 sodium, and that's where quite a lot of the sodium in the world comes from. Or it can spit out a neutron and turn into a slightly light version of magnesium, 2312 magnesium. So there's a number of different pathways, and these manufacture from the carbon those other elements, neon and magnesium being 2 of the common ones, some sodium and some oxygen, but there was probably oxygen present already in these carbon oxygen cores. So that can happen, and that accounts for why we see some of these elements, the neon and the magnesium particularly, in the spectra. Now that's important when we have a think about these stars blowing up, because sometimes instead of a traditional type 1a supernova, we see an event called a type 1ax. These are the explosions of white dwarf stars that don't completely destroy the star. They are subluminous. They don't emit in as much light as a traditional type 1a. Now, they're not very common, and in fact, PA30 looks like the remnant of a 1ax event, and perhaps the only one that we know in our galaxy. We've found a few candidates for this in other galaxies, but this one's far nearer and much easier to study. Now, one of the other ways that these type 1ax events can occur is by helium accretion. So normally you would have a binary system where hydrogen from the outer layer, unused hydrogen from the outer layer of the giant companion, spirals over onto the white dwarf and triggers a type 1a supernova. But if the companion star is not a traditional red giant star, but something hotter and more violent, like a Wolf-Rayet star, where it's already got rid of all of its hydrogen, then it's possible that as that comes to the end of its life, it is helium that flows over onto the white dwarf companion. And that can have a different effect. Instead of just accumulating and maybe occasionally there being nova bursts of hydrogen turning into helium, you can reach the point where you get sufficiently hot that helium itself starts to fuse, and you get 2 heliums making a beryllium and another helium then making carbon, and then another helium making oxygen. So suddenly you can release a lot of energy by consuming several helium nuclei and fusing up to make more carbon and more oxygen. Now, that can produce a very powerful nova event that is not sufficiently powerful to disrupt the entire core of the star. That would only happen if the carbon and oxygen started undergoing fusion themselves right throughout the core. But this can happen to the helium that is accumulated and is being fed by the companion. The normal hydrogen runaway, in a typical situation where there's hydrogen present, does produce nova events. They're quite bright, but they're nowhere near as powerful as you would get from the result here. The helium event is going to be delayed because it's much harder to trigger the helium fusion reaction takes a lot more extreme conditions. And so the buildup has got to go a lot further before it will do this particular job and suddenly consume all the helium in a very violent event. And that may well be the result or the cause of these type 1ax supernovae. Now, as I said, the other thing that XMM Newton showed was that we did have the presence in the nebula of neon and magnesium, but we also saw heavier elements, silicon and sulfur, and those are evidence of yet further fusion reactions. So 24 magnesium plus an alpha particle, a helium nucleus, makes 2814 silicon and some gamma radiation and energy. And you can take two oxygen atoms, and if you smash those together hard enough, you can make 3216 sulfur, and again, gamma rays and energy. And it suggests that in PA30's case, we've already gone to this stage and seen these. Plus, we have the evidence of yet further isotopes being made, including that nickel 56, which may well be evidence that there have been a very powerful amount of fusion going on here. And so you can get one of these very violent nova events, I'm going to call them, a type 1ax explosion that doesn't destroy the star, that does create a supersonic shock wave, creating fusion in the nebula itself of the matter that's been hurled outwards, creating elements going up the periodic table, neon, magnesium, things like silicon, sulfur, and even a little bit of the metals, nickel and iron can result. But it doesn't destroy the entire core of the star. What it tends to do is give that a very big kick, and that can hurl the zombie star out away from the explosion at high speed. And we often see these hypervelocity white dwarf cores traveling at very great speeds that don't seem to make any other sense. So these are probably zombie stars. Zombie because they've been brought back from the dead. The supernova explosion should have destroyed them. And possibly what is happening is that you then get material from the expelled nebula falling back and reaccreting onto the zombie core, waking it up again. But what can happen there is that those heavier elements sink, and the heaviest ones are the densest nuclei sink to the core. And as they do so, they might build an iron core white dwarf, very rare star indeed. And these would be much smaller and much denser than typical carbon oxygen white dwarfs, which might be half a solar mass the size of the Earth, or oxygen neon magnesium white dwarf stars, which might be just over one solar mass and considerably smaller than the Earth. But these might be very, very dense white dwarf stars indeed. And so PA30, its central star, may indeed be the first discovery of a zombie star. And that's where I want to leave this one. We might talk more about zombie stars and indeed stars with iron cores that don't collapse later on in another video. But thanks very much for listening to this one.